This is the review for graphing different types of equations, and the equations that we're going to look at in this video are the ones that are in a fraction form. So I have an equation written here. So y equals 2x squared over x squared minus 1. So the first thing you want to do when you see any equation like this is, first of all, let's do the pre-calc stuff. So for the pre-calc, if you set the bottom, so bottom equal to 0, right? So x squared minus 1 equals 0. So x minus 1, x plus 1 equals 0. We find that when x equals 1 or x equals -1, there will be a vertical asymptote. So I'm going to write, so the bottom tells vertical, that's important, asymptotes. Okay. And then obviously if the bottom tells the vertical asymptotes, then we can compare the top and the bottom to find the horizontal asymptotes. So the rule is that if these two are the same, not those two, if this and this, the two largest exponents are the same, then all you have to do is you take the leading coefficient. So we have a 2 in front here, then we're going to have 1 in front. So 2 over 1 equals 2. So then we know we have a horizontal asymptote at y equals 2. So that doesn't help us with graphing for our purposes, but I always like to do that whenever I see a fraction first, because in case I mess up a step along the way, it'll help us out. So just if you know how to do those already, great. If not, it's just a good way to check yourself. You can do this without knowing how to do that. I find it helps. So what did I say? X equals -1, x equals 1, and y equals 2, right? So I'm just going to leave those in the bottom right. So when we're graphing, we can look and see that those are our asymptotes. So our first step is we're going to find the first derivative of this equation. And obviously this equation is going to be a quotient rule because we have the division sign, or it's a fraction. So we have bottom. And if you don't remember how to do the quotient rule, I have another video up from the last test that goes over the quotient rule and the product rule and the chain rule, just in case you need a refresher on that. So I'm just going to go through it quickly right now. If you need to recall how to do it exactly, step by step, I made a whole nother video for that. So we have bottom, so x squared minus 1 times the derivative of the top, so 4x minus the top times the derivative of the bottom, so that's going to be 2x, okay, all over the bottom squared. Okay. So that's our first step, is just writing that out. So our second step is going to be to try and simplify this. So what we're going to do is we're going to try and distribute. So obviously we got a binomial here with the x squared minus 1 and the monomial with the 4x. So we're going to distribute it like this. So we can do 4x times x squared. So we got 4x cubed. And then minus -1 times 4x equals -4x. Okay, now we go to the other side. So this time this is going to be minus, because we got the minus here, that's where that minus comes from, minus 4x cubed. And then we have all over the bottom squared still, x squared minus 1 squared. And look at that. If you notice, we have a positive 4x cubed here and a negative 4x cubed here. So we can go ahead and we can continue to simplify. And that's going to happen a lot for what we do, is we're going to have something on the top or something on the bottom that's going to cancel out. So always make sure as your third step, if your first step is finding this, your second step is simplifying this, your third step should be to cancel out. So third step should be cancel out. So we can cancel this out with this, and we're left with -4x over x squared minus 1 squared. Oh, terrible squared. Okay, that is our first derivative. Before I erase that, I'm going to just go right to the second derivative test, not second derivative test, finding the second derivative. So next, after we do all that, so this is our final for the first derivative. We got to move on to the second derivative. So to find the second derivative, what you want to do is you want to take the first derivative and you're just going to take the derivative of the first derivative. So you're probably like, what? You're taking this number that we just found. Remember, this number was the derivative of this equation. And you're taking the derivative of this, right? So it's going to be another quotient rule because it has the division sign, the fraction. So we have the first, bottom, x squared minus 1 times the derivative of the top, negative 4x. Sorry, just had to sneeze there. So we got bottom times the derivative of the top minus the top. Messed that up. Got to be very careful, and that's why it's important to follow along. So we got bottom times the derivative of the top, so that's going to be negative 4 minus the top, so it's going to be negative 4x times the derivative of the bottom. So how do we take the derivative of the bottom? It's x squared minus 1 squared. Well, if you notice, is that normally we'd have something like x squared, but because the x is being replaced by this, it's actually a chain rule. Again, there's a whole nother video on explaining when to use the chain rule, explaining how to use the chain rules, going through it step by step. So I'm just going to do it quick. So we're going to bring the 2 out into the front. So we get 2 times whatever this is, 2 times x squared minus 1. And then 2 minus 1 equals 1. So that's raised to the first, but we can get rid of that because that's that can be omitted. And then we have to chain on the derivative of what's in the parentheses. So derivative would be 2x. Okay. And then of course all over bottom squared. So you can write x squared minus 1 squared like that. But if you remember your rules about exponents, if you're raising an exponent to the exponent, you can really just multiply. So then 2 times 2 get you 4. So we see that this is raised to the 4th power. Okay, so that's step 1 for your second derivative. It's getting a little messy here, so I'm just going to try and erase what I don't need. Oh, you can always go back and check the work if you need that. So now we have that. Now we're going to move on to our second step, and I'm going to put it below. So our second step is always going to be to try and simplify it in some sort of way. So when you have this second derivative here, first thing you should look for is, especially when it's a big mess like this, is to try and cancel something out. So you'll notice that this term, and this term all show up on every part of the equation. Now you might be saying to yourself, what if it was only here and here, but not here? Say this wasn't there, okay? Could you still try and cancel it out? No, you can't, because it needs to be in every single term. Because these are separated by a subtraction sign, you need one on this side and this side for it to be able to be factored out. And I'll show you why just in a second. So the way that it would work is on the top, it would pull the x squared minus 1 out. And that's kind of like taking a common factor, a greatest common factor, and pulling it out. So then you'd be left with another x squared minus 1 times negative 4 minus negative 4x times. Remember, if we pulled this out, so this got pulled out to here, right? So we're just going to be left with 2 times 2x. And then that's all going to be over x squared minus 1 to the 4th. And we'll see that this can cancel out with one of these to leave us with the 3. Okay, so now that we have that, we can continue to simplify. It's getting a real mess here. So you know what I'm going to do? I'm going to, what can I do? I can erase this. I'm going to erase the work for the first derivative. So if you need to see that, you can always go back. Just to clear up space, because these problems take a lot of space. And then I'll just, before I erase that, I'll write negative 4x squared minus 1. Okay, so now we got our first derivative all written down. So now we're to the point, I'm just going to rewrite this up here. I'm going to just draw a little arrow so you see. You're left with x squared minus 1 times -4 minus -4x, sloppy, times 2 minus 2x. Sorry, 2 times 2x. Sloppy handwriting on here is starting to mess me up. All over the x squared minus 1 cubed. So then we can go to our next step, which is obviously to just continue to simplify. So we'll distribute this -4 in. So we got -4x squared plus 4 minus 4x times, this is going to be 4x. So it's going to be 4x times 4x. It's going to be 16x squared. So it's going to be minus 16x squared over x squared minus 1 cubed. Okay, so now that we have that, what we can do is we can just do the final simplification to get -20x squared plus 4 over x squared minus 1 cubed. That is the answer to our second derivative. So I'm going to just erase this work real quick. If you need to see it, you can always go back, but I need space in order to do the rest of the problem. And obviously, it's taking me a little bit longer to do this because I'm going through it, and I'm trying to just go slow, just so you understand how to do every single step. Trying to make it as easy as possible. So let me just rewrite -20 x squared plus 4 over x squared. It's weird that it came out that abnormal of an answer. I hope I didn't make an arithmetic error while I was going through that. But nevertheless, you know what? Let me just double check. Just double check something. So we have, I haven't done this problem before, so I'm just going off what I did on the presentation. So I hope all is fine. Don't remember going over this one, so I'm not. I guess I'm just gonna have to trust that that's right. We can check the graph at the end to see and make sure that it's all fine and dandy, but nevertheless, if there was an arithmetic mistake, it's just the same process. Sometimes I just can't add 1 plus 1. So we're going to move on. Now that we have our first and second derivatives, we can do the first derivative test. So what we're going to do is we're going to do our number line. That's supposed to say first derivative test. Our second number line, second derivative test. And then we're going to do our little graph underneath. And I swear to God, if anybody forgets to put X and Y on their graph, I'm saying it now and I'm making a big deal about it right now. Do not forget to put X and Y on your graphs, because that will be the stupidest point that you can ever lose. And it's just a terrible feeling because it's something stupid to get points taken off for. So X, Y, can't emphasize that enough, X and Y on your graphs. You need to have that for every single graph that you draw, X and Y. So for our first derivative test, what we're going to do is we're going to set the top equal to 0 in order to find our potential turning points. So we have the top equal to 0. So that would be X equals 0. And then our bottom equal, so this would be our potential turning points. That's what PTP stands for. And then we got our ponds, which are points of non-differentiation. Essentially, when you have a division like this, you know that the ponds are going to be asymptotes, because remember we did that with pre-calc earlier down here, and that's exactly why I did that. So we should see that the pond should be equal to our asymptotes. So we'll find that when we set this equal to 0, what will give us the bottom equal to 0? It'll be X equals 1 and X equals -1. And we just go back and check that that's the same thing there. It should be, because obviously that's where our asymptotes are. So we're going to plug this on our number line for the first derivative test. We've got -1, 0, 1. Okay. We can do our first derivative tests. So we need to, let me just erase this here just to keep it clean. We need to test a number out here. So let's say -2. If we think about this, if we're plugging in, we'll get -8 on top. -2 squared, so that's going to give us 4. 4 minus 1, that's going to be positive. So it's going to be a negative over positive. So it's going to be a negative. So it's going to be decreasing. And then we need a number in between -1 and 0. So let's just think about it. A good trick is that we know that anything, if this, here's a rule. Here's the rule. I didn't go over this. Here's the rule. If it's raised to an even number, 2, 4, 6, 8, whatever, even number, it will always be positive. So if I gave you x squared, no matter what number you plug in for x, x squared will always be positive. And that makes sense, right? Because if you have the graph x squared, it looks something like this. At no point does it ever go negative. So we have our bottom here, it's all squared, so we know our bottom's always going to be positive. So now we can just look at the top. So if the top's negative, it's going to be negative, and if the top's positive, it's going to be positive. So if we plug in a negative number, we're going to get negative times negative, right? Negative times negative. So then we're going to get a positive number. Does that mean that I messed up? Well, I might have messed up this one then. What? -2. I did mess that up. I did -4 times 2 instead of -4 times -2. So you should get a positive number here, not a negative number. So that should be increasing, right? Because -4 times -2 equals a positive 8. And then a positive over a positive, because remember we said the bottom's always going to be positive because it's raised to an even number. So it's going to be increasing, increasing. So then we go on to the positive side. So if we did a negative times a positive, right? Because anything in here would be positive. It's going to be negative. So it's going to be decreasing. And then obviously farther out, it's going to be the same thing, decreasing. So how do we write our intervals of increase, decrease? So increase, we can see that we're increasing from -infinity, right? That's out here, -infinity to -1. And what type of bracket are you going to use? Well, what you have to do is you have to look up here and you see that -1 was actually a pond. And the rule for ponds is if you have a pond, it's always a soft bracket. It's never included. Whether it's in the first or the second derivative test, doesn't matter. Ponds are never included. So we got the soft bracket there in union with -1 to 0. Now, will that be included or not included? So we see that it starts positive and goes negative. So that's actually a turning point. So our turning point would be at 0. And then when x equals 0, we can go back and plug into our original equation. We find that y is also equal to 0, right? Because we get 2 times 0, so we get 0 on the top. 0 divided by anything is going to end up being 0, as long as the bottom's not 0. And then that's going to be a hard bracket because if it's a turning point, it's always going to be included. Decreasing interval, it's going to be 0, again, hard brackets, to 1. But 1 is a pond, so it's going to be a soft bracket in union with 1 soft bracket. And then infinity is always a soft bracket. So that's our intervals of increase, decrease. And that is our whole first derivative test done. So now we're on to our second derivative. So we're going to follow the same process that we did for the first derivative test. We're going to set the top equal to 0. So we end up getting -20x squared plus 4. It's going to be, something's not right there. -4. Something got messed up. Let's look at this. 2x squared. X squared minus 4. Okay, yeah, that got messed up. It's only the top that's messed up. The bottom is good. The top got messed up. So how did the top get messed up? It should be, let's see, bottom. So x squared minus 1 squared times derivative at the top. So it should be -4 times the derivative, or times the top, sorry, -4x times the derivative at the bottom. So it should be 2 times x squared minus 1 times 2x all over the bottom square. So x squared minus 1, 4. This is going to cancel out. This is going to become 3, and then this becomes canceled out. So then that gets left with -4x squared plus 4 times the -8, still getting -16x squared. Does it just not work out? That could be that too. Need to do this. Trying to figure out what is not working out here. That should be working. Oh well. Let's see. Oh, that's what it is. The numbers are right. I'm just silly and I'm trying to overthink this. So what's going to happen is you're going to have, no, that's not going to happen. Why is that happening? So if you had 20x squared or -20x squared plus 4, so you get -4 equals -20x squared over -20. You can get 4 over 20 equals x squared. No, give you a negative number there. I'm not sure why that's giving you a positive number. My apologies for trying to figure out the mistake here. X squared minus 1 squared. You can always just fast forward through this part. It's just me double checking my work. -4x minus the top. Oh, that's not going to be 4x. It's just going to be times -4 times the derivative, or times the top, -4x times the 2 times x. I think I know where the mistake was. Times 2x. I'm pretty sure I know where it is. So then we're going to get 3 on the bottom. This is going to cancel out. This is going to cancel out. So we get -4x squared plus 4. And then that should be plus, right? Because we got the minus, plus, or no, that's still going to be times. That's what it was. It was the sloppiness of the whiteboard that was throwing me off. So it's going to be plus 16x squared. So then we end up with 4 plus 12x squared. There we go. So it's going to be 12x squared, not 20x squared. And that should be a token for you to write neatly, because I thought one of my multiplication signs was actually a subtraction sign. And it's a good way to actually figure out if you made a mistake in your calculations, because if it comes out where you're trying to take the square root of some crazy number and it's going to come out not as a whole number or not as an imaginary number, then we know, oh, almost did it again. That should not be a negative, that should be a positive. So now we can set the top equal to 0 to find the potential points of inflection. Okay. And we see that when we set that equal to 0, we get 12x squared equals -4. X squared equals -4 over 12. And this was what I was trying to show you before. When you take the square root of this, look at this. You got a negative inside the radical And we find out that there are no potential points of inflection that are real because you're taking the square root of that negative of a negative, and you cannot do that because that's an imaginary number. The 0 with the line through it just means that it's an empty set or there's no points of inflection. It's good to know. And then the bottom, we can do our ponds. We end up getting that x equals 1 or x equals -1 when we set that equal to 0. It's the same thing. So we just plot that back on our number line and do our tests. So -1 and 1. So we plot that back on our number line, and we're going to do the second derivative test. So we're going to look for a number out here. Let's think about this. If we have a negative number and we plug it in for x, we're going to get a positive here, right? Positive plus a positive over a big positive minus a small negative. So we're going to get a positive, if I believe, and that's going to be up. If we plug in 0, right, because 0 is right in the middle. If we plug in 0, we're going to get 4 over -1 cubed, so it's going to be -1, so it's going to be a negative. And that's going to be down. And then anything greater than 1, we're going to end up with a positive. So my big question for you is, are -1 and 1, first of all, are they turning points? And second of all, are they points of inflection? And the answer to that should be a big resounding no, because ponds are not points of inflection, and they are not turning points. So then we can do our intervals of increase, decrease. I know there's a lot of work here that I'm just going through, and this video is taking a little while, but I'm just trying to go in depth, and I had that one little mistake that took me a little while just to catch. So just hopefully you followed along until now. So we're going to have from -infinity to -1 in union with -1 to, sorry, that's not in union with -1. It's in union with 1 to infinity, right? Because we have anything on this side is positive up till -1, and then anything on this side is positive up until 1. And the rule for points of inflection or ponds, actually, because these are not points of inflection, they're ponds, is that it's a soft bracket, right? Ponds always get soft brackets. So then we go to where it's decreased. So we see it's right here, and we see that it's between -1, soft bracket because it's a pond, and 1, soft bracket because it's a pond. So now we will go to our graphing. So we have our x and y labeled. Label your x and y axes. Can't say that enough. We'll do the pre-calc stuff, so we can put in our asymptotes right here at x equals -1. Never hurts to label the equation for your asymptote. Give you some good brownie points. X equals 1. And then we have the asymptote at y equals 2. Y equals 2. Okay. And make sure when you're labeling them, y equals 2 because it's horizontal line, x equals 1 because it's vertical line. So we have our asymptotes here. So now we need to look at these derivative tests, and we see that the first one is positive, concave up. So it's going to be something like this, right? Because a concave up graph is like this, a concave down graph is like this. So it's concave up because it's pointing this way. And then obviously if something is a positive increasing slope, it's going to be like this. And if it's a negative decreasing slope, it's going to be this, positive, negative slopes. So then we go past -1, and we see that from -1 to 0, we are going to be positive. So it's going to be positive slope, but concave down. So, oh, and we also have a turning point at 0, 0. I forgot to add that. See? That's why it's good to have it written down at the thing. Turning point at 0, 0. It's good to have a point of reference just to work from. So we have positive concave down. So it's going to look something like that, right? And then from 0 to 1, it's going to be negative concave down. So it's going to be like that. And look at that. We see that it's a turning point. And then we can go past 1 here. So we have negative. So it's going to be a negative slope. and it's going to be concave up. So where can we do a negative and a concave up? It's going to be, let's see, if we tried to draw it here, how could we draw a negative and a concave up? It would look something like this, right? But you see that that doesn't make sense because you got the asymptote lines right here. So you're going into the asymptote lines. So we know that it's going to be on the other side of that asymptote. So negative concave up, it's going to look something like this. And it's the perfect symmetry on this graph. And that can be checked because if you plug in 1, so this is a quick check if you want to just tell if it's symmetrical or not, plug in 1. So 2 times 1 equals 2. And then over, sorry, don't plug in, you can't plug in 1 because it's fun. Plug in any positive number. So let's say 2. So 2 times 2 squared, so 2 times 4, it's going to be 8. 8 over 4 minus 1, 8 over 3. So it's going to be 8/3. And then if you plug in -2, you should get the same thing. So it's going to be 2 times 4 is 8 over 2 times 4 minus 1. It's going to be 8/3. Yep. So if you plug in a negative value and then the positive value that's the same magnitude as it, so like 2 and -2 or 3 and -3, or even if you did x and -x and they come out to be the same answer, you can tell that it's symmetrical, meaning that it's symmetrical over the y-axis. So these are all the steps for the ways to graph anything that's a fraction like this. I think I touched on everything. Just let me double check this. Got the asymptotes, intervals of increase, decrease, up, down, ponds. Yeah, I think we touched on everything. So I'm going to make another video just to show the last type of ponds that aren't using asymptotes. So it's either going to be a shark fin or a just a sharp point or even a point of vertical tangency. But for now, that's all the steps in order to do the fractions like this. As you can see, it's a lot of work, but it's easy to check your mistakes. You saw that I made the mistake here, just the arithmetic error. And I was able to just double check it because I knew that there wouldn't be a point of inflection here just sensibly because I had all the pre-calc rules. So I already kind of knew what the graph would look like because after the pre-calc, I knew where the asymptotes were. And then worst case, if you completely lost, you can just double check and say, let's say this value is -2, you go back, plug -2 in here. Right? And you'll see that it gives you the value right here. So if you really need to just double check, you can always just plug back in X values and find the Y values for each of them. Besides that, I'm going to start on the next video for the last types of graphing. And you can always go back and double check the work if you need to just be refreshed on how it was happened. Anything else? You should be good for this. This is probably, I don't know. I find this one more difficult than the next type, but some people find it easier because it's, even though it's more time consuming, it's easier to check and make sure that you got right just 100%. So I'm just going to leave you here and good luck.